Okay, let's try another example. How about the line integral over the curve C? Let's just draw the circle this time for fun. Just don't read anything into that circle. You can draw it or not, as long as you have a closed curve. But it doesn't mean you have to do anything different. Okay, of what? Of y times sine of x dx minus x squared dy, where C is the triangular curve. Let's draw a picture to describe the curve. So, let's draw that axis better. Okay, there's the axes. Here's pi on the x-axis. There's pi on the y-axis. The triangular curve is actually, sorry, that should be straight. Just 3 line segments oriented counterclockwise like this. If you really want a challenge, why not pause the video, try it on your own, and then unpause to see if your work looks the same. Okay, so here's the answer as I'd like to give it is, how about we have to slightly rewrite the problem, integral over C of y sine of x dx. But I'd really like to intentionally have a plus sign here to match the plus sign that's in the Green's theorem. So then negative x squared dy. Yeah, so then we'll identify the same notational pieces that are in Green's theorem, that would be, so y sine of x is going to be capital P, and then negative x squared is going to be capital Q. And if we apply Green's theorem, we're going to have a double integral over a region D. But what is that region D? Let's just draw a picture of it. That region shouldn't be too hard. Yeah, so it should be, there's pi on the x-axis, there's pi on the y, sorry, that's not the x-axis, oh my goodness. There's pi on the x-axis, pi on the y-axis, and then this line segment that goes this way. And we fill in. Yeah, so this is a picture, this filled in triangle is a picture of D. So you'll notice we've got to make some distinctions, whether filled in or not. So here, there's a triangle, sure, but it's not filled in, and we're just talking about walking around the perimeter of the triangle, and that's C. Then we have here the filled in triangle, and that's D. Okay, so then this, of course, this line we could write as y is equal to, slope is -1. So how about pi minus x would be an easy way to write an equation for that line. So then we'll have here, in this spot, we need, as Green's theorem tells us, we need here partial derivative of q with respect to x. So look at this negative x squared, and when you differentiate with respect to x, you'll have negative 2x here. Then copy the minus sign that's in the theorem box up there, so we'll have a minus. And then in this next spot here, we need partial derivative of p with respect to y. So right there, we're going to stick in partial derivative of p with respect to y. So staring at that's p right there. The derivative with respect to y is going to be sine of x. Okay, close parentheses, dA. Now, the point is, we can take this problem, sorry, the work is getting in the way, and we can now write this as an iterated integral. Right here, it's just as a double integral. It's written just over the shape, but if we were going to actually compute, we should write integral sign, keep the integrand here, negative 2x minus sine of x, dA. Let's go ahead and write as dy dx. Of course, you could do it the other way around, but I just wanted to write the dy first, really just simply because we've solved for y here. So y goes from 0 to pi minus x in the picture, and then x goes from 0 to pi. Right? Yeah, 0 to pi right there. Okay, we will skip some of the actual work here. It's not bad. You can do it, but in the end, you should get as a value here negative pi minus, I believe, pi cubed over 3 would be, this would be a final answer numerically. It can be done. The integrals are not so bad. Let's just comment that the notation that's here, okay, the notation, the circle is basically used, this notation is used to mean that C is counterclockwise or is positive orientation.